Okay, thanks, Nick. And thanks to the committee for inviting me. So I'd like to talk to you today about some work that I've been doing with a PhD student in my lab, Jeremy Berg. And this is some work developing simple approximations to describe the coalescence with soft sweeps, i.e. the coalescent where selection occurs on standing variation. So typically when we think about sweeps within populations, historically, we've been thinking about a set of haplotypes within a population with some pre-existing set of neutral mutations standing in the population. A selected mutation arises on one of those haplotypes, and under the full sweep model, the classical sweep model, that allele is immediately beneficial, increases in frequency, dragging with it the haplotype on which it arose, dragging with it the allelic diversity on the background on which it arose. Some of those alleles are going to go to almost fixation, but due to recombination events during the sweep of the allele through the population, they won't hitchhike all the way to fixation, and diversity is reduced in that region. Okay, so if we're thinking about this in a coalescent model, how we think about this is that at the selected sites, there's some very shallow genealogy where all of our lineages are forced to coalesce back under the selected mutation. As we move out along the sequence, away from the selected mutation, as you all know, we start to encounter recombination events, and those recombination events correspond to lineages recombining out of the swept backgrounds, coalescing much deeper in time, allowing diversity to accumulate on these lineages, and so diversity will recover as we move away from the selected sites. So for example, here's a plot just showing you levels of heterozygosity, moving out from the selected sites along the genome. Diversity at the selected site is 0 for both types of sweeps under two different selection coefficients. But the recovery of diversity as we move away from the selected sites is much quicker when the selection coefficient is smaller because there's much more time for recombination. Okay. So the model that people have developed as a simple way of thinking about this is that there's some allele sweeping through the population following logistic growth, and that allele takes roughly TS generations to transit through the population. So at the selected sites, all of our lineages are going to be forced to coalesce TS generations ago. Okay, what's happening to first approximation as we move out from the selected sites along the sequence? If we're at a neutral locus some genetic distance r away, then each lineage has an approximately independent probability of recombining out of the sweep. And that probability of recombining out of the sweep is approximately the amount of time that there is since the sweep started, TS, times that recombination rate, divided by 2. And that factor of 2 is there simply because the trajectory is symmetric around a half. So that's a simple approximation to the probability of a lineage recombining out of a sweep. Okay, so if we think that each lineage has an independent probability of recombining out of the sweep, then the number of lineages that our selective sweep forces to coalesce is going to be binomial with this probability of each lineage recombining out of the sweep independently. So the probability that I lineages recombine out of the sweep is simply the probability of drawing I coins with heads with this probability. So this is a very simple approximation to describe the coalescent process under full sweeps. And a number of authors have developed more sophisticated approximations to this process. But we're just going to stick with this simple expression for the moment. Okay, so that gives us the level of diversity at a distance r away from the selected sweep as simply the population-scaled mutation rate times the expected coalescent time for a pair of lineages. So if we're looking at the diversity between a pair of alleles sampled in our population, that's simply equal to the population-scaled mutation rates multiplied by that underlying pairwise coalescent time. Assuming that TS is very small, there's no chance for the accumulation of diversity of lineages that fail to recombine out of the sweep. So that's simply equal to pi the background level of new pairwise diversity, times the probability that one or other of our pair of lineages recombine off the selected backgrounds. And so this exponential recovery of pi, as we move away from the selected sites, can simply be seen as the exponential probability that our pair of lineages fail to recombine out from under the sweep. So that's a admittedly crude approximation to the effect of hitchhiking for a pair of sequences, but it gives us good intuition for how these parameters, for example, the time it takes the allele to sweep through the population, and the recombination rates, interplay into describing the patterns of diversity around a selected allele. Okay, so the thing is that selection doesn't always act on new mutations the moment they enter the population, right? We can have cases where there are actually multiple selected alleles at a locus, each one of which is present on a different haplotype, and when selection switches on, those different instantiations of the selected allele increase in frequency such that the population is fixed for a selected beneficial phenotype, but no one of these alleles has gone to fixation. So we can get a case of a soft sweep rather than a hard sweep, where different copies of the differently derived copies of the selected allele have increased in frequency at the same locus, each one of them taking the haplotype on which it arose to intermediate frequency in the population. But at the selected site, no one haplotype has gone to fixation here, due to the fact that the different mutations were on different haplotypes. The other way in which we can get a form of a soft sweep is if our mutation has been segregating in the population for some amount of time before it became beneficial. So let's imagine now a single copy of our selected allele segregating in the population, and that allele has been at low frequency for some amount of time before it then becomes beneficial and gets to sweep through the population. During the time while that allele has been segregating in the population at low frequency, that allele can have recombined onto different backgrounds, and then, when that selected allele races up to fixation, it takes with it those different backgrounds it was present on up into the population, but once again, no haplotype has gone to fixation in this larger region. Okay, so those are two different types of soft sweeps that people talk about in the literature, and there's been a bunch of work on developing those models and simulations. So during today's talk, I'm first going to tell you about what we've been doing, developing simple approximations to selection on standing polymorphisms. And then later on in the talk, if I have time, I'll tell you about some work we've been doing, looking at selection on multiple mutations, and thinking about the model with recurrent selective sweeps, featuring selection on multiple mutations leading to soft sweeps. Okay, so just to motivate this a bit further, there's a number of great examples which we now know of, where it's clear that the beneficial allele was segregating in the population for some amount of time before the allele became beneficial. So for example, in the case of the EDA change, underlying this change in armor plating in these stickleback populations, it's known that this large effect allele affecting the plating in these freshwater populations was segregating at low frequency in the marine populations. Similarly, frequently during domestication, rather than a new allele being responsible for some beneficial phenotype during domestication, plant and animal breeders have made use of standing variation. So there's a number of great cases of selection on standing variation in domestication, such as this allele underlying this phenotype associated with the TB1 change. Okay, so what we're thinking about is an allele segregating in the population over some relatively long time periods, and that allele is potentially neutrally evolving, or maybe just balanced at low frequency in the population. At some time in the past, that allele has become beneficial, and the allele was at frequency F in the population when the allele became beneficial, and that allele has then swept up to fixation. Okay. So thinking again about that cartoon of the haplotypes within the population, what's happened is our selected allele has recombined onto multiple haplotypes, and I'm showing you here those different haplotypes that the selected allele has recombined to on the left-hand side of that beneficial allele in different colours here. And those different haplotypes have been swept up to intermediate frequency. Okay. So, there's two different phases to this process. There's the selected phase, where the beneficial allele has formed a relatively large population of roughly 2n individuals, where n is the diploid population size. And assuming that the mutation has been segregating at a frequency f over some amount of time in the past, there's a relatively neutral phase where the allele is being present in 2nf copies within the population. Okay. So, in order to think about properties of genetic diversity in the region surrounding this sanding variant that's gone to fixation, I'm going to argue that the majority of the information present in the data is contained in the genealogy at the selected sites. And that's how we usually think about these processes, right? There's some genealogy at the selected sites, and then we think about recombination on that genealogy as we move away from the selected sites. Okay, so here's the genealogy at the selected sites. Everyone's sitting under that copy of the mutation that arose and spread through the population. As we move out from the selected sites, we can have recombinations on that underlying genealogy. And that's going to describe patterns of genetic diversity as we move out from the selected sites. So the first class of recombinations that we can have occur in this selected phase of the allele, where the allele's been moving from frequency f up to fixation in the population. So that's a potentially relatively short time span. And let's think that that time span is roughly TS generations. Assuming that there's no neutral coalescence in this phase, once again, we can think about a probability of a lineage recombining out in this selected phase. And I'm showing these special lineages recombining out, each one a special little coloured star, pinging out of that trajectory through the population. So we're going to have an independent probability of lineages recombining out during that selected phase. Okay, so after those lineages have recombined out during the selected phase, at some distance r away from the selected sites, we also have the genealogy of our remaining lineages in the population that have failed to recombine during the selected phase. Okay. If we're moving out from the selected sites in the population, and we're looking at these recombinations that occurred in this neutral phase when the allele was segregating at low frequency in the population, effectively what we're doing is we're moving out, looking at recombinations once again on that underlying genealogy, and the different haplotypes present in our population as we move out from the selected sites correspond to different recombinant clades in that underlying genealogy. So here I'm showing you as hitting that first recombinant haplotype in the population as we move out from the selected sites, and that corresponds to this recombination here in this phase, corresponding forward in time to a recombinant haplotype which is hitchhiked to low frequency in our sample. Moving further out, we hit a recombinant haplotype which hitchhiked to a higher intermediate frequency in the population, corresponding to a recombination that sits above a clade of individuals in that small genealogy at the selected sites. Moving further out again, we hit more recombinants corresponding to different recombinant ancestors of these clades. Okay, so what we're looking at when we're looking out from the selected sites is we're looking at a collection of haplotypes formed by recombinations on that little underlying genealogy at the selected sites, corresponding to clades of lineages which have recombined out from that tree. Okay. So what we're going to do is we're going to develop a simple set of approximations to describe the coalescent process in this latter phase, and then use that as a way of thinking about the properties of recombinations during that neutral phase. In particular, we're going to make use of this simple result from Carlson from back in 2000s. So if we think about a neutral population, the rate of coalescence is roughly 1 on 2n per generation per pair of lineages in the standard coalescence. If we're thinking about an allele which has been segregating at frequency f in the population for some amount of time, and imagine that this time is relatively long compared to the depth of this genealogy, then if we're thinking about the coalescent in that class, the rate at which pairs of lineages are forced to coalesce in that small population 2nf individuals is simply given in expectation by 1 on 2nf. Now, Carlson, back in this paper in 2000s, shows that this is the right expected rate of coalescence, but it doesn't have the right variance if we use this to parameterize an exponential. But I'm going to argue for simulation that turns out not to matter too much, and that we can think about coalescent times in this subpopulation made up of this derived allele segregating at low frequency as simply corresponding to a coalescent process in a population of 2nf individuals. Okay, so that's also not a particularly great approximation, and a number of people back in the late 90s and early 2000s developed nicer approximations, but analytically less tractable. Okay, so we're thinking that for a pair of lineages, their coalescent time in this little population made up of 2nf individuals is simply given by 1 on 2, the exponential, with rate 1 on 2nf. If one of these lineages is to recombine, then a recombination event has to occur before they find a common ancestor, and that lineage is going to have to recombine out of this population. If we're at a distance r away from the selected sites, then recombination occurs at a rate r per generation. And if the frequency is relatively constant at f, the probability it recombines off the derived background is simply given by 1 minus f times r. Okay, so this suggests a simple approximation for the probability that either of my pair of lineages recombines out of this derived class before they're forced to coalesce. And that's simply given by the rate of recombination for my pair of lineages, 2 times 1 minus fr, divided by the rate at which they coalesce, plus the rate at which they recombine. Okay, so this gives us the probability that our pair of lineages fail to coalesce in this derived phase of the trajectory because one or other of them recombine out, and instead they're going to coalesce at much greater depth. So first thing to note is that this is ignoring recombination in this selected phase, but it's easy to include that, and we'll do that in just a moment. Okay, so we can write down the pairwise diversity, the amount of diversity we find sampling a pair of alleles in our population, simply as the level of neutral diversity that we'd expect in this region if there was no sweep. And the only way that we're going to get that neutral level of diversity is if one or other of our lineages recombines out of the derived trajectory before they're forced to coalesce, and then they'll coalesce at this much deeper time and have this level of diversity. So the level of diversity, a distance r away from the selected site, is equal to that neutral level of diversity times the probability that one or other of our pair of lineages recombines out from the trajectory. Okay, so that's a crude approximation to describe what we'd expect to see in patterns of diversity as we move away from a selected allele at frequency f in our population. What I'm plotting for you here is a demonstration that this actually works quite well in describing levels of diversity in our population. I'm plotting on our x-axis the recombination distance, moving out from the selected sites, and I'm plotting for you the recovery in diversity as we move away from the selected sites for alleles which are segregating at 5 different low frequencies in our population. And in the squiggly solid line, I'm plotting for you the simulations under MS for that parameter model, where we simulate fully stochastic trajectories. And in the dotted line, I'm plotting for you our simple analytical expression for diversity as we move away from the selected sites. So it agrees quite nicely. OK. We didn't include recombination in the selected phase in that expression, but it's easy for us to go back and add that in. In order for our pair of lineages to escape the sweep and coalesce deep in time, having a neutral level of diversity between them, they can either recombine in the neutral phase or in the selected phase. So the probability that they do either is simply 1 minus the probability they fail to recombine in this stage, multiplied by the probability they fail to recombine in this stage. And that's simply the expression we derived before, modified by this recombination rate in that selected phase. OK. So we now have an expression for diversity as we move away from a selected site which was present at a frequency f previously in our population. However, we'd like to go further than that and describe levels of diversity in terms of higher order summary statistics. We might, for example, wish to describe the number and distribution of haplotypes segregating within our population as a function of the distance from the selected sites which is swept through the population. OK. So let's think that we're a distance r out from the population, from the selected sites. And what we want to know about is the distribution of the number of haplotypes that the selected site is present on, those number of haplotypes which the selected site is dragged up to intermediate frequency in the population, and their distribution. That's equivalent to asking about the distribution of this colouring which we've painted on these haplotypes here. That's equivalent to asking about the number of recombinations on that small underlying genealogy at the selected sites, and the number of the descendants of these recombinant clades in our sample. OK. So once again, first of all, ignoring recombination in this initial phase of the trajectory and just concentrating on recombination in this phase of the trajectory, what's nice is we're, under this simple cartoon model, we're simply asking about the number of recombinant haplotypes on this small underlying genealogy. And that's equivalent to asking about the number of types and their frequency in a Ewan sampling formula on that underlying genealogy. So what we're doing here, right, is we're looking back in time at these lineages, coalescing together, and recombination events in this simple cartoon model corresponds to alleles in the infinite alleles model. Because every time there's a recombination out, that corresponds to a new allele, a new recombinant haplotype. OK, so in order to describe the number of haplotypes and their frequency in the population, we're simply looking at the Ewan sampling formula with a scaled parameter 4nr f1 minus f. And there we're simply thinking about the scaled rate of coalescence in this subpopulation, which is 1 on 2nf, as before. And once again, there's this rate of recombination corresponding to alleles moving out of this derived class, which occur at rate r1 minus f. OK, so that's describing a simple approximation to the distribution of the number of haplotypes segregating in our sample. Once again, we're initially ignoring recombination in this first phase of the trajectory. So let's see how that does.
So, are we zooming in here on haplotypes that are short enough so that there's not going to be many recombinations? Like recombinations are going to be kind of unlikely?
So we're assuming any number of recombinations out to this point, right? So what we're doing is we're looking at these recombinations falling on this small tree here, right? So if we move further out, the recombination rate's higher. That corresponds to recombinations occurring further down on this tree, recombining those haplotypes out, right? So we're not making any assumption about the underlying recombination rate here, I think. We're just putting that in as a parameter. Whether we actually get to see these underlying haplotypes is going to depend on patterns of diversity, right?
Wait, so if it recombines out, but then recombines out again deeper in, then don't you?
Yeah, so here we're ignoring double recombinations back into this environment. So we're assuming that F is low, such that if a lineage is lucky enough to recombine out, it doesn't get to recombine back in.
Right. No, that makes sense.
And that seems like a fair approximation when we're
that's
usually thinking about F being low. Okay. So what you're looking at here is a set of simulations and our analytical predictions for the probability of the selected allele which has gone to fixation, ignoring recombination in that selected phase for the moment, the probability of the selected allele being on J underlying haplotypes in a sample of N. So for example, out here, we're looking at the selected allele being present on 3 haplotypes, while here we're looking at the selected allele being on just 2 haplotypes. And we're looking at, as a function of the recombination rates, as we move out from the selected sites, and we're looking at that for 2 different underlying frequencies that the selected allele was at when selection turned on. Okay, so the different colors correspond to the selected allele being on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 haplotypes. And once again, the solid lines are simulation-based, and the dotted lines correspond to our analytical theory based on the Ewan sampling formula. So close to the selected sites, both the simulations and our approximations say that the selected allele should be present only on a single haplotype, because there's very little opportunity for a combination. As we move out, we see the selected allele is more likely to be on 1 haplotype, 2 haplotypes, 3 haplotypes, and so on, as we move out from the selected sites. And also we see if the frequency of the selected allele was higher in the population before selection turned on, we see that we quickly decay away from the selected allele being present on a single haplotype and quickly find the selected allele present on additional haplotypes as we move out from the selected sites. And once again, we see pretty good agreements between our simple approximation and our analytical prediction and our simulations. In this case, it's not altogether perfect, but it's still doing a pretty good job in describing the haplotype distribution as we move out from the selected sites. Okay, so given the distribution of haplotypes within the population, under our model where we assume we get to see those haplotypes, we can then switch and calculate basic other summaries of patterns of diversity as we move out from the selected sites. So for example, we can think about the number of segregating sites that our selected allele is present on as a function of the recombination distance from the selected site. So to do that, we simply need to think about how many different clades of individuals our selected allele gets to be recombinant on the background of. So we can sum over the probability that our selected site is present on I distinct haplotypes over N, and conditional on being present on I distinct haplotypes out of N. There's I distinct haplotypes which contribute to diversity in our region, and so then we're simply taking the number of segregating sites, conditional on there being I underlying draws from the population. So we can write our number of expected number of segregating sites as a function of this underlying distribution of the number of haplotypes in our population. So what you're looking at here is that number of segregating sites. And here, once again, we're looking at our simple approximation developed based on this simple cartoon model of how selection and standing variation works. And in the solid line, you're seeing the predictions based on MS simulations. So once again, we see that there's quite good agreement, though by no means perfect, as there does seem to be a slight bias, in the agreement between our approximation based on this simple cartoon model of the genealogy at the selected sites and simulations under MS. Okay. So we can extend this approximation to describe what we'd expect if we allowed recombination to occur during that selected phase as well. In that case, once again, we can assume that each lineage has an independent probability of recombining out during that selected phase, and those remaining lineages which fail to recombine out during that first phase of the trajectory are going to coalesce according to this infinite alleles model. So we can count up the number of distinct recombinant haplotypes which our selected allele is present on at a particular recombination distance from the sites.
One sec. Actually, it's about the previous part, so don't answer if it pulls you back. But
do you want me to go back, or?
Well, I'm just wondering if you also neglected the mutations that happen within the F by the same.
Yeah, so
by the
we're
same
explicitly ignoring mutations during this part of the trajectory. So we're implicitly assuming that this is a very short time compared to the
coalescent time.
and to the coalescent time in the population, and that seems to be doing an okay approximation. So this approximation is going to start getting worse and worse, right? Potentially as that allele starts becoming more and more common in the population. In that case, the coalescent times within that derived class are going to start resembling those in the larger population. And so these approximations are going to break down. And also this approximation that lineages recombine out of the derived class is also going to break down. They're assuming they don't recombine back in. Okay. So we can also, in this case, when we allow recombination in the selected phase and in this neutral phase, write down the probability of our selected sites being present on J haplotypes in a sample of N. Now, we allow our haplotypes to first of all have an independent probability of recombining in the selected phase. That corresponds to a binomial probability of the number of haplotypes that recombine in this phase. So we're assuming that I lineages, I haplotypes, fail to recombine in this phase. In that case, we can work out that they also then have to recombine out in this later phase, and we can simply sum over whether recombinations occur in this first phase or this second phase to describe the number of recombinant haplotypes present in our sample. Okay. So this simple approximation gives us a way of thinking about the distribution of haplotypes segregating in our sample after a selected site has just gone to fixation. It's nice because it gives us relatively simple analytical expressions for these parameters such as pairwise diversity and number of segregating sites as simple functions of that underlying frequency of the selected allele when selection began and the time at which it swept through the population. It's also nice because it starts to suggest ways of doing inference on models of selection on standing variation due to the simple form of this model that we're proposing. So using these ideas, we're starting to develop simple inference methods to try and estimate parameters such as the strength of selection and the frequency of the selected allele when selection began, thinking about the number of haplotypes that our selected site is segregating on at various distances from the sweep. So as a first step towards doing this, although admittedly it's very provisional, we started to develop simple approximate likelihood formulations to calculate the likelihood of a particular time of the sweeping through the population and the frequency it was segregating at, thinking about if we could actually observe these underlying haplotypes segregating in our population. And to do this, we use the simple product of approximate conditional likelihoods, similar to that in Lee and Stevens, to calculate the probability of a set of colorings of these different haplotypes. As a first approximation to say, if we could actually observe these underlying haplotypes, could we hope to actually estimate F? Or is it intrinsically a hard problem, and so it's not worth developing further approximations? So we're doing this What I'm showing you here are a set of simulations, and we've simulated under a set of different true F parameters, 1%, 2%, 3%, 4%, 5%, corresponding to the frequency that the selected allele was segregating at in the population before selection began. And using the simple approximate conditional likelihood, similar to Lee and Stevens, we've assumed we can observe the set of underlying colorings in the population and estimated this F parameter. And what I'm showing for you in each case is a set of simulations at a particular true F value, and I'm showing you our estimated MLE and confidence intervals based on that likelihood surface we construct using Lee and Stevens. So we can see that even if we observe the underlying coloring of these different haplotypes within our population, we're doing a really quite poor job of estimating this parameter F, assuming that we have far more information than we likely do have, assuming that we have access to these underlying haplotypes. We see that there is some correspondence between our estimated F and our true F, and in some cases we're probably quite good at excluding the idea that the selection turned on the moment the allele started in the population. F is 0. But beyond that, we're going to have really quite a poor job of estimating that underlying frequency.
A comment, if you don't mind.
Sure.
It's well known that when you have a sweep, you have a kind of stochastic phase at the beginning where where it's not so different from neutrality. Then there's a deterministic phase, almost in effect. And then, so because of that stochastic phase, when the sweep takes off, is going to be, the frequency may be quite different from the initial F.
Well, so the initial stochastic phase, right, depends on how strong selection is.
Yes, selection is only moderate.
Yeah.
That deterministic phase is going to kick in at a place where you don't really know what F is.
Yeah.
So I suspect that's...
Although, to be honest, here we're thinking about F being something that's well away from the boundary, right? We're thinking about F being 1%, where even weakly selected alleles are going to behave deterministically above 1%. But, I mean, the general point is, right, that we're going to have trouble estimating this parameter. There are going to be lots of situations where sweeps on standing variation, if the frequency is low, are going to look quite like sweeps from new mutations simply because of that stochasticity in that initial phase of the trajectory.
I was going to say, but isn't the real question, is it a soft sweep or a hard sweep?
Yeah.
Can you use this as the basis for a test?
Yeah, so I think we can use this as a basis for a test of whether F is 0. And I think we're going to do a reasonably good job of excluding F as 0 in some cases. But to be honest, having gone through all of this, basically, if F is high enough that you can tell it's not 0, you're probably not going to see much of a sweep anyway, right? So in some sense, it's going to be hard to estimate and separate whether there's a sweep. If it's a sweep from standing variation where you can say it's a sweep from standing variation, you probably can't estimate how quickly it transited through the population. Or you can estimate that it transited through the population quickly, but you're not going to be able to estimate F because it looks like a hard sweep even if it started from low frequency.
But I guess where the complication is the dominance coefficient of the beneficial allele, right?
Yeah.
So sweep on a recessive allele will make
Yeah, so if there's selection on a recessive allele, it's going to be even more complicated. And in some ways, one of the reasons for doing this and developing these simple analytical approximations is just a way of making this point that even if we get to observe far more information, such as the genealogy of the selected sites, the colorings of these haplotypes, there's still incredibly little information for us to extract about this. So if we try and do this using real data, putting in the complications that we don't get to see the genealogy, we don't get to see those haplotypes, it further complicates the problem.
As additional leverage, if you have a second population or a time series population, how much does that help?
Yeah, so from Steve's talk, right, if you have a time series, you potentially do get to see more of that trajectory. The problem is if your allele has been segregating at a frequency of, say, 1% in the population, unless you've got very large ancient samples in your Carlson in a few years' time, you're not going to get to see those alleles segregating, right? So alleles are going to be coming up from relatively low frequency, could still be standing variation in our population, but we're going to miss them unless we have very large samples in the past, right? If you have a second population, you might get to see that allele segregating in that population, and that's interesting as well. But once again, there's a broad parameter range while this allele could have been present at 1 in 1,000 frequency, where we're not necessarily going to get to see that in the present day sample, right?
What if you catch it in the phase in which it's increasing in frequency?
So if you capture it in a partial sweep in one of the populations?
In the period before, between when it's at 1% and at high frequency.
Well, in that case, so if the allele's partially swept into the population, right, and you've been lucky enough to catch it on its way to fixation, or it's somehow over-dominant so it's trapped in the population, you basically have the same problem as you have here, right? In this case, we talk about the allele sweeping up to fixation in the population. If I told you that it just swept 20% frequency in the population, we'd still be in a similar state where we get to talk about recombinations in that phase where it's sweeping to 20%,
So
say.
you have these 2 time points. You have the points where it's at 20% and the points where it's fixed. And
Yeah.
But fixed at perhaps a number of different haplotypes which are all coordinating the fixing or something like that. I'm just
Yeah, so I think that, there is more information to be gotten from time series looking at these alleles, right? That's definitely going to be true. That's going to increase the amount of information you have. But it's still fundamentally difficult to distinguish whether an allele is sweeping from low frequency or from a frequency close to 0. We're still, as Nick was pointing out, there's still this stochastic phase at the start of the selected sweep where the combinations can occur. We're sort of getting some amount of information about that by looking at patterns of haplotypes in these different populations or different time points. But there's still a lot of uncertainty about that underlying genealogy at the selected sites.
Yeah, I was going to ask you, is there an effect of sample size here? So if you were able to sample thousands of individuals, and you get a much finer resolution on all of those recombination events and new mutations that have arisen very recently and in the past.
Yeah, so I mean, if you
presumably would get better resolution on what
but still the problem is, so if you're thinking about getting to sample thousands of individuals, right, they still coalesce in remarkably quickly, and you're still looking at a few, recombinant clades. Those clades are now very large, but there's still inherent stochasticity in the size of those clades because of that underlying coalescent process, right? Okay.
Hi, I was wondering about the appropriateness of applying the UN sampling formula. So if you say there's no mutation, it means that or if you assume there's no mutation, it means that you're assuming recent coalescent, which means that you're assuming a small population size. But my understanding of the UN sampling formula is that it holds in situations, or one of the assumptions is that you have large N. So I was wondering if you're worried about the ASF or the UN sampling formula breaking down in the scenarios that you're looking at, which is small population size.
Yeah, so it is a concern, right, that we're thinking about this small population. However, this small population of 2NF individuals, that may still be large enough for the coalescent to hold, right? So if N is large, even if F is relatively small, such as 1%, this may still be a very large number of individuals who are carrying the selected allele. As we decrease that frequency down towards 0, we are going to run into problems with having a very small number of individuals, and there's going to be a stochastic population size here, right? But in that case, individuals are going to be coalescing incredibly rapidly, whether it's under the coalescent or under the Fulbright-Fisher model, right? There won't be much time for a combination, and we'll be in that phase of being back in a full sweep. Okay, so... Sure. I've given up on getting to the second part, so yeah.
Because you are not talking about the strength of selection.
So the strength of selection, right, is all in that TS, right? It's all in the number of lineages that get to recombine out in this phase.
They don't matter.
Well, they do. They're going to be singletons in the sample, right? If we think there's no coalescence in this phase. There's a set of lineages that get to recombine out. That's parameterized by TS. This number of lineages that get to recombine out in this phase. So there'll be a set of singletons, and how many they are as you move out from the selected sites is going to be determined by the strength of selection. It's going to be determined by that time the allele transits through the population, right? And so that was what I was saying about, I think there's a confounding that we'll either be able to estimate something about the strength of selection because the allele came from low frequency, we get to estimate how quickly it went through the population. or we'll be able to say that the allele was present as standing variation because F is non-zero. But at least for contemporary data, in that case, we probably don't get to estimate the time at which it transited through the population, simply because most of the recombinations occurring in this phase rather than this phase.
Well, again, if you want to go on, that's fine.
No, I've pretty much given up on
So I think you made the mistake of giving too interesting a talk.
Yeah, well, the problem is I've given this half before. I haven't given the second half before, so I was excited to get to that, but I should remember to flip it in the future.
Yeah, we probably. Well, one more question.
Okay.
So what happens if you use data in aggregate for many sites together? So you look around, just an arbitrary idea, around all substitutions of a certain type.
Yeah. So we're thinking about doing this actually in maize, where they have a number of potential domestication alleles. And in that case, we're thinking about learning in aggregates about the properties of selection and standing variation for domestication alleles. But also we could potentially do this in aggregates for all, say, non-synonymous sites, just to pick a class at random. But then we'd have to think about haplotype patterns rather than just pi, because pi is, not a way of deconfounding F from the time at which these alleles transit through the population.
But how well would it do, I guess, would be the question, or if you have a sense, or...
It will do better than nothing, but yeah. I still think it's hard to estimate these parameters, right? Okay.
Okay, thanks, Fred.
Thanks.